All right, so we're starting on 47, and the reason we're doing this is this level of mathematics, it's very proof-based, but this level of mathematics is, number one, how people can use math to essentially predict the future. So Galileo did this with falling objects, which is what 47 is about, but also Einstein used this level of math, this proof type stuff, to really predict the future with like relativity and things like that. So, long story short, if you're going to go into high academic math and physics, this is the stuff that you could be doing. Obviously, it's kind of an upper level problem, so I'm not going to make you prove stuff on the test. So please don't panic. So 47 says, for an object falling freely from rest, show that the distance traveled during each successive second increases in the ratio of successive odd integers, 1, 3, 5, etc. This was first shown by Galileo. Okay, step one, what in the world are we doing? So let's draw a picture. Okay, so we've got a ball, and we drop it from whatever distance. So we're going to call this T0. So then it falls a little bit. We'll call this T1. After 1 second, it's fallen that far. So then we know it falls a little bit further. We'll call this T2. And then it falls even further. T3. I'm going to switch to lowercase t's because that's what I'm supposed to do. It's more typical. Anyway, so this is the position of the ball at time equals 0, time equals 1 second, 2 seconds, 3 seconds. So what is this question asking? So this question is asking if you were to take this distance right here from T1 to T2, it is going to be a ratio of an odd integer from this one. And you can do that same pattern with this distance to this distance. So concept, that's what we're doing. So to get us started, we're going to start with my physics people for a position function. We've got a change of x equation, right? Somebody read that one off to me. It's the v. Is that right? Initial velocity times t. Oh yeah, VIT. There you go. I didn't have my formula sheet in front of me. Sorry. So this is what's on our formula sheet, but we're starting at, somebody took a ball and then dropped it. So what is our initial velocity? 0. So that's going to make our life a lot easier. So now let's talk about our position, and then we can go from there to start solving some stuff. So we'll use y. We're going to change this to y. So our y of 0. My math people, you good with that phraseology? So that's the y position at time equals 0. We plug that stuff in. We've got, what's our acceleration again? Negative 9.8. We're just going to stick with g. But at time equals 0, where are we at? It starts up here. So I'm just going to abbreviate that and do 0. Okay, so then y at 1 second. So now things get a little more interesting. So we're at 1/2 g. What's our time? 1 squared, which we can simplify to 1/2 g. Are we good with that? Okay, let's just do 2, because why not? So at 2 seconds, we plug and chug 1/2 g 2 squared, which then turns into 1/2 What's 2 times 2? Okay, so 1/2 g times 4. But hey, look at this. This is the same as this. Right? Okay, so then I'm going to do some clever math, and I'm just going to say y of 2 equals 4 times y of 1. Okay? So I just took this equation and I plugged it in for there. And we're going to use this to find the pattern later on. That's why we're doing it. Are we good for that? So let's do one more. We're going to do y of 3 equals 1/2 g 3 squared. Are you guys cool if I skip that center step? So then we can do some math. We got 9 times y of 1. Right? So right here, this is the same as this right there. We good for that? Okay, but let's go back to, we are trying to compare this distance to this distance, or this distance to this distance. So we're changing colors. So we can say that any one of those distances is going to be like, let's say if we're looking at this distance right here. So in order to find this distance, using only our position functions, how would we find it? Have I lost you? Okay, how would we find this distance if all we had are position functions? We know this point, and this point. How can we find this distance? What do we think? So we can find this distance, we can find this distance, we can find this distance. Cameron, it helps when you're looking. Thomas, it helps when you're looking. So if we wanted just this distance, what would we do? You would subtract this one and this one. Okay? Does that part make sense? So the distance traveled during each second can be found by subtracting 2 adjacent position values from the above list. And I pulled that one straight out of the solution manual. But what that means is, let's say we wanted to find distance at time equals 1. So we want this distance. Okay? So we can take the position function, y1, I pulled that from right here, and just to create a pattern, we would subtract this one from it. I get it, T0, a whole bunch of zeros, but it's going to help us establish a pattern. Are we good for that part? So, okay, this is 0, so this equals just y1. So let's do this again at 2 seconds. Okay, so now we want this distance. Well, actually, this distance right there. So in order to find that, we need the position at T2 minus the position at T1. Does that statement make sense? Okay, so that's what we'll do. We're going to say y of 2 minus y of 1. So let's see here. If we plug in stuff from here and here, we're going to have, let's see here, we're going to have 4 y1, I pulled that from here, minus 9 of y1, and I pulled that from here. So I took my two position functions and I just substitute them in. Are we good for that? What? Why am I using y3? What are you talking about? Oh, you're talking about... That's a good question. I didn't mean to do that. Good catch. So my y1 would just be y1. Thank you. That was a very good catch. Thank you, Zach, for paying attention. Okay, so simple algebra. We can pretend that this is 4y minus y. What is that going to add up to? So this equals 3y of 1. Okay, we're going to do this one more time just to make sure that we get a pattern. So we're going to switch to green now.
I switched to green.
Good job. So the distance for T3, we want this distance, so we're going to take this whole thing and we're going to subtract this. And that will leave us with just this. So when we do that with position functions, that's going to be y of 3 minus y of 2. And here's where we're going to use, I should probably move this. Whee. So y of 3 is this guy. So 9 times y of 1. Okay? Y of 2 is 4y of 1. Okay? 9y minus 4y. 5y. So are we seeing a pattern here? So because of how the formula works, every time we square a number and then subtract it from the previous distance, we're always going to get an odd integer. We start with, there's an implied 1, 3, 5. And I'm not going to write out exactly the rest of the proof, because for me, if you were to just go through this on and on and on, you're going to be able to find that each one of these coefficients is going to be an odd integer. So, therefore, we have proven that the value is always going to be an odd in the sequence of 1, 3, 5, 7, so on and so forth. So this form of abstract thinking is how we actually push technology into the future, because the math predicts what can and should happen, and then the technology catches up with it. Because Galileo and Einstein is my favorite example. Einstein was able to predict relativity very, very accurately. And now, how many of you have phones that have GPS? So that GPS operates off of Einstein's equations. And Einstein came up with them long before satellites even existed. So that's essentially the power of math. Any last minute questions before I end the video?